There's been an abundance of conspiracy theorists and their debunkers on YouTube, namely the resurgence of flat Earth. Now with that comes a whole slew of other conspiracies. Space denialists, moon landing hoaxers, chemtrail guys, so many more. If you do a quick search on YouTube for people debunking them, you'll find plenty. But the problem is, most of them are only surface level. Anyone can prove that the Earth is round or that the ISS is not just a mock-up in a pool somewhere. If you want to explain to a conspiracy theorist how a rocket engine works in space, you're going to need, well, this. Scary, scary, scary math. And unfortunately, not many people are willing to do that. I know someone who can. I know someone with a degree in aerospace engineering, a love of space travel, who knows quite a lot about rockets, and is willing to do horrifying math. Oh, this is going to be disappointing.
5, 4, 3, 2, 1.
Morning, everyone. I'm the pressure-fed astronaut, here to deal with moon landing hoaxers, space denialists, and to talk about rockets and space travel while doing so. Now, normally, this is where I would introduce the big conspiracy today. Who am I debunking? What's going to be debunked? What do I want to focus on? But don't have anyone for that today. Instead, I'm just going to introduce myself, lay out some of my qualifications, who I am, and then have a little fun at the end. Hi, I'm the pressure-fed astronaut. Again. Now, while I'm not filled with helium nor actually an astronaut, I do have a degree in aerospace engineering, which should mean something. See? So as you can see, I got it from the University of Minnesota, and because of my interest in space travel, I took every class I could while there. Both, to be exact. Now, it's disappointing, but on the side, I did have a big interest in space and space travel, so I did plenty of research on my own. Now, what I also did during this time was a senior design project sponsored by the National Institute of Aerospace called RASC-AL. RASC-AL is an acronym for Revolutionary Aerospace Systems Concepts Academic Linkage. It's a design composition sponsored by the National Institute of Aerospace with judges from NASA, Blue Origin, other NASA centers, Aerojet Rocketdyne, folks like that. You kind of get the picture of who I'm talking about here. And for that, I and a team of 7 others designed a propellant resupply system for future Mars missions. What is that? Well, if you're going to Mars and you want to reuse the spacecraft, you got to fill it up with fuel again. So what the team and I did was came up with a system that could do just that. We even partnered up with a university that was designing a propulsion system for these future Mars vehicles that we would refill. So that was another theme. There were 4 themes in the competition: propulsion system, habitat, resupply, and then a polar sample return from the moon. That's boring. And there'd be, competition was for the different themes. You had to compete with the other universities doing the propellant resupply capability. And of those, only ours won. We're the only one that made it, apparently. I don't know why, but we were. And I've linked our final presentation down at Cocoa Beach in Florida in the description, so you can watch that and get really, really disappointed in me. Now, on the side, like I said before, I do enjoy researching space and rockets. Now, before you cringe and go, oh God, he's just another Elon fanboy, he's like, oh, rockets are cool. I like the ones with the boosters, and, kind of just talk about it like that. No, I like going in depth. I want to know the decisions, why there are boosters, why there aren't boosters. I'm not like the other girls, I guess. Oh, and for our project, we won Best in Theme because we're the only one. We also won Best Logo. Our design, well, is Cislunar Electric Transport and Utilization System. It's named Cletus. And during that project, I did learn quite a lot. I didn't just learn the fun things like, hey, you can launch these things. Here are the different depot concept designs you could do. It was more working with others, making design decisions, fist fighting your partner university, nicely, of course. The real world engineering, not just doing math on a whiteboard and crying, which is quite fun. But we're going to change gears. I want to change gears now. What do you expect from me in this channel? I'm going to debunk people. That's it. I'm going to find Jeranism, explain to him why there isn't a camera on the moon. Live feed. It's a waste of money. So we'll do that. We'll do kind of your basic debunk, right? I'll show a clip of the guy saying something dumb. I'll go, hey, you're dumb. And a little explanation why. But everyone does that. What I'm going to do that's different, not like the other girls, is I'll do some engineering. I'll do some explanations of things more in depth, right? So our next video, Jeranism does ask, why isn't there a live stream from the surface of the moon? You can easily say he gives like 12 reasons and they're all stupid, but could you do it? And I'll be focusing on that. I'll design a lander to actually do that mission. We'll see if it can do that or not, if it actually works. And then maybe I'll branch off into, talking maybe personal opinion pieces, because, as we all know, the guy on the internet has an opinion, and you want to know it. Then there's other subjects, maybe talk about, space and film, what's right, what's wrong, mostly wrong, or looking at other things. Maybe some space history. I do want to talk about spaceflight history, since a lot of people don't actually do that. And it'd be really interesting to actually talk about how we got to where we are today. And my big interest, of course, is the private launch industry. What happened before SpaceX? Because there's a lot, and no one talks about it. So, all right, okay. I'm trying to think. There's got to be something else. Okay, so we got, I have a degree. I'm not like the other girls. I like big rockets and I cannot lie. Something else I'm missing. What am I missing? What am I missing? Let me look. What's... Oh. You know what? I'm going to prove to you that rockets work in the vacuum of space. Let's do that. Okay, so this is a really complicated problem. I'm not going to just dive straight into the scary stuff and expect you all to follow me in. That's not a good thing to do. So instead, what we'll do is start with the very simple things, the very, very, very basics. And then we'll build up to the complicated math. Because, if you don't understand what's going on, down here, how on earth can I explain to you the complicated things? All right? Good? And yes, I can't dress myself. That's just sad. All right. So the common complaint of the conspiracy theorist with rocket engines working in space can be broken down into two parts. The first one is, what's burning? Right? What's actually being burned here? Where's the air? There's no air in space. And then because there's no air in space, this is the second part, why isn't there, what's it pushing against? What's the rocket pushing on? Well, what the rocket's pushing on is a bit more complicated. So let's start with the simple side of the problem. What's burning? Okay, well, I think we all learned this at some point in school. If you didn't, well, congratulations, you're going to learn now. We'll look at the fire triangle. It's a triangle for, burning things. So, you need three basic things for fire. First one, oxygen. It's in our air, it's 21% of the atmosphere. It's good, fun stuff. You need that to burn. Now, what actually is burned, right? Wood, paper, other things that burn, plastics, your neighbors. Right? That's what we call fuel with a really big F. Okay, so there's one half, so you need these things. And of course, the third part is, I'm in oxygen right now. I'm not on fire. So what do we need? Well, we need heat. Voila! The fire triangle. Now, there's also some folks who go into the crowd of, ooh, there's actually a fourth one. It's a tetrahedron. It's 3D. You need the right conditions. But that's just being pedantic. We have these things. So, okay, where's this in a rocket engine? Well, it's easy. Just carry it with you. It's all there. Now, the misconception comes from how your car works. In your car, you have the internal combustion engine, right? You have gasoline in your fuel tank. It's pumped into your piston. It's mixed with air. It's coming from the atmosphere. It's pulled in. And then you have a spark plug. Ignite it. Kaboom, pushes the piston down, drives the car, keeps going. The rocket engine is basically the same thing. That's all it is. I'm serious. Here's a rocket engine. Oh, that's horrible. Okay. They look pretty much like this, but not as ugly. So what I have here is the combustion chamber. This is where the kaboom happens, and we have gases flying out. So you get your fuel, and you got your oxidizer. Heat's in here. So we have here, so we're carrying the fuel and the oxidizer with you. So it's just like your car if you carried an air tank. That's pretty much all it is. Okay, so I know what you're wondering. What's actually being burned? So we're going to take a look at a few common propellants, as they're called. So this is me being pedantic here, but it's not rocket fuel unless you're referring specifically to the fuel. It's called the propellants, because you actually have oxidizer and fuel. There's two things, but that's just me being pedantic. So here's a few combinations. If you're a big fan of SpaceX, they use liquid oxygen and RP1. RP1 is just a fancy grade of kerosene. That's all it is. Yep, so we have liquid oxygen, that's our oxidizer, and then RP1 is our fuel. Another one that's really common is liquid oxygen and liquid hydrogen. This is what the space shuttle runs on. SLS will be running on this. The Centaur upper stage. A few other rockets use liquid hydrogen. It gets really good performance, but it's really cold. It needs to be really cold. It's low density. It's awful for everything else. It's really mean. One that's being phased out, this is a hypergolic combination. It's dinitrogen tetroxide, also known as NTO, and then hydrazine, but specifically unsymmetrical dimethylhydrazine or monomethylhydrazine, UDMH. These are being phased out for a few reasons. Notably, they're toxic, horribly toxic. UDMH smells like fish, and it'll give you cancer. Nitrogen tetroxide isn't nice either. I think it burns your lungs and eyes and doesn't like your nervous system. That's pretty much one of the reasons why they're being phased out. They're just toxic. One being worked on right now that SpaceX and Blue Origin are working with is liquid oxygen and methane, CH4. Methane doesn't need the special refinements as kerosene does, and it does get some better performance, but again, we're kind of being general here. An interesting one that the British used was hydrogen peroxide and kerosene. But you kind of get the point where I'm getting at here. There's plenty of things you can burn, especially with liquid oxygen. It does not like things. It'll burn anything. Not as much as liquid fluorine will, but liquid oxygen likes burning things. Okay, so your rocket carries liquid oxygen and its fuel, or oxidizer and fuel. So, for example, if you look at this picture of an Atlas V, you'll notice there's some ice up here. That's the liquid oxygen tank, because liquid oxygen has to be cold. Because right now, air is gaseous oxygen. You need it to be a liquid, it's got to make it really cold, right? So you have liquid oxygen up here, then kerosene's down here. And they burn them, they mix them together, they burn. The heat for the combustion is done through the ignition system, and once it's ignited, it's pretty much going to keep burning unless something goes horribly wrong. Now, these are liquid bipropellant rockets, because it's got two parts, and they're liquids. There's also solid rockets and hybrid rockets. Solid rockets you can buy in a store. Firecrackers are pretty much solid rockets. Model rocket engines are all solid. Usually it's like ammonium perchlorate and something else in them, the little aluminum binder. They're neat, they're dense, and you can't really transport them very well because they're explosive. You just mix the oxidizer and fuel together as part of the kaboom, essentially. And you just light them off, you can't turn them off. And hybrids are either a liquid oxidizer and solid fuel separated, or solid oxidizer and liquid fuel. Mostly you'll see liquid oxidizer and solid fuel. There are solid oxidizers you can use, but they're all really, really scary to work with. So for example, the most common hybrid you'll see is nitrous oxide, spelled with an H, of course, NOx, and then rubber. They're rubber of some form. You can build these at home. You can buy nitrous oxide. It's really expensive because you can get high off of it, but I shouldn't say that. Redacted. Then for the solid rockets, you'll see AP, which is ammonium perchlorate, hydroxyl terminated polybutadiene. I've only read that, so I don't know if it's pronounced that way. And then our aluminum binder here. Ammonium perchlorate's toxic, makes chlorine in there. So like our space shuttle rocket, solid rocket boosters, they burn these. Pretty much all solid rockets burn these. There's been some alternatives investigated, and you can make one at home, not with this, but you can make one out of sugar. You get some potassium nitrate, which is found in fertilizer, and some sugar, and you make a sugar rocket. I tried making one once, and it killed me. So now we got the basics. So pretty much the fire is made by bringing in an oxidizer and a fuel. You mix them together, they go kaboom. Cool. Now on to the harder part. Okay, so we've established that a rocket engine can burn things in space. It carries the things it burns. You don't need to breathe in air or do anything magical. You just carry it with you. So now we've got that established. What exactly is being pushed against? Right? That's the big question. Where does thrust come from? Well, if you take a look at our rocket engine, very simplified. So you have here the combustion chamber, and you have this thing here. That's a nozzle, and that's scary because this isn't your everyday nozzle. It's a magic nozzle. But with this, if you do this though, you're going to notice something interesting. That's just a bucket. So we're going to approximate this all to a bucket, right? It's a kaboom going off in here, right? All wants to get out, it's going to get redirected out that way. So we're going to approximate this to a bucket, a firecracker in a bucket. If you've played with fireworks and gallon ice cream buckets, you know what I'm going to do here. What we're going to do now is, if you've taken a high school physics class or any kind of physics class, is a free body diagram. We're going to take an object and draw the forces acting on it, and then hope you can do some math to figure out different values at where. Okay, so we're going to draw two buckets. One's going to be on the surface of the Earth, and one's going to be in space. This will be just like our rocket engine. Okay, so first we'll draw the one on Earth. So here is our bucket. Very crude drawing. And then we're going to light off a firecracker in here, right there. Okay. That's our firecracker. It's the exact center, and it's going to make a big spherical kaboom. Perfect combustion, perfect everything. And our bucket's also going to have some magical properties where There's nothing else in there. It's just a firecracker going kaboom. It's a magic vacuum. The other thing we're also to take note of here is the bucket is going to be a perfectly rigid body. It's not going to wiggle, because if we did that, it's going to be scarier. Okay, so here it is. Here it is on Earth. Okay, so now we're going to draw the forces acting on it. Now there's a few that act on it before the explosion. So first we have Earth. Earth's got gravity. It's pulling you down. Force equals mass times gravity. So it's pulling the bucket down equally this way. But since our bucket isn't moving, Earth's pushing back upward at the same force. It's as simple as that. Then the air's pushing on it. You have some air pressure, right? Down like this, over in. Okay, we'll make these smaller because atmospheric pressure is going to be small in this case. Okay, so this is pre-explosion, and I'm just going to make a note here. All these vectors are the same size. I just can't draw. Now we're going to have a big kaboom. Now, I said it's going to be a spherical explosion, right? Out like this, it's going to make a circle, but because of fancy things called trigonometry, you can just approximate it to up and to the sides. So our kaboom is going to go up, over, down, and it's going to reflect up because the Earth's pushing back up. All right, so these are all the forces acting on our Earth-based bucket. Now we can do eliminations, right? Okay, well, these are the same size and going in the opposite direction, so they can cancel each other out. These are all the same. We can get rid of those. That goes away, this one goes away, this one goes away. So it leaves these two. Now, because of the way I've drawn this, air pushes down a little bit, and kaboom pushes up a lot of bit. So now, just add them together. This is vector addition. This goes away and eats up a bit of this. And voila. The sum of forces, upward. That's it. This is on Earth. Okay? Because on Earth it's easy, right? There's air, there's all these other things that conspiracy theorists like to talk about. So let's redo the problem. All right, so now that we've established it works on Earth, what's going on? We'll put our space bucket in. Again, we have our glorious bucket shape with firecracker. What external forces are acting on our bucket? Absolutely none. It's just the kaboom. So now, it's going to go boom, 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 boom. This is where it gets weird. So we've already established these go away. Now, what's going on with this? Well, this isn't actually like that. It's actually little gas particles, because that's what's going on, right? Like a firecracker, it doesn't go poof and disappear. It makes little dust particles, right? It's little particles. So those are all going to be going outward. That's where the force comes from. Well, some just going to get thrown out the bottom. Okay. Others reflect up. Reflect up like this, right? It's going to generate force. So force ends up going this way. Ignore that one, that's an old one. Now, this we'll discuss in the math section, but the fact that there are particles leaving, just going out the bottom, actually generates some force, which actually makes our kaboom force twice as powerful by this drawing. So actually a rocket engine will work better in space, and that's kind of obvious because there's nothing else pushing on it. So, right? So we're going to do a force diagram on our little rocket engine here. Not this one, of course, but we'll do that just so we're all clear. Just so we're clear on the operational side before we get to the math. Okay, so here is our glorious combustion chamber. This is just a drawing. Real ones are completely different in shape and size. So you notice I actually left the bottom out because, again, like the bucket, there's no bottom. It's empty. So what happens in a rocket engine? You have oxidizer and fuel somewhere else in the rocket. They are injected into the combustion chamber, where after an ignition of some form, they mix and burn. This generates high temperatures and pressures, which over, up, down, they're pushing against the walls of the rocket, even on the nozzle. We'll talk about nozzle later, but this is what's going on. Now, of course, these cancel out, and this goes away. Not really, but, right, so we have this gas going out. And force goes up through the combustion chamber, right up on the injector head. So that's where the force comes from. This is what's happening. We good? Pause here. Take a deep breath. This is what's going on. Now, math. Okay, so we've established on the simple side, fireworks in space. You can do it. You're not going to start a fire just by throwing ethanol and a spark plug up in space. But if you carry oxygen with you, then you can. Now, we also described on a force level, just basic diagrams, how a rocket engine works, why it generates thrust. Now we're going to get into the math side of things. Okay, so we have thrust, but what's this number? How do you generate thrust? What's the math involved? Does this shape of the combustion chamber that I have not drawn mean anything? Do the gases mean something? What's the numbers? Where do we come up with these things? And I know some of you are sitting in your comments writing, well, actually, math is not a way of describing reality. It does things you can do. You can pick an equation to describe anything. And yeah, that's kind of true, but these equations we'll be just talking about here work. They're a great way of modeling a rocket engine. Now, when you start getting down to like the nitty-gritty, they don't actually do it very well because the real world exists and fluid mechanics and thermodynamics are all witchcraft when you get down to it. But for what I'm doing, this is the very, very simple physics. It works. It's a good approximation for what we're doing. And I'm not here to debate philosophy with you. Go do that somewhere else. Go be wrong somewhere else. So, first things first, what is force? No, we're not talking about Star Wars because Disney will sue me. So force can be most described easily as F equals mass times acceleration, right? Your weight is Earth's force on you. Your mass and the acceleration of Earth's gravity. For me, I weigh like 175 pounds on Earth. Earth's force is 175 pounds on my body, right? So if you divide by 32.2, you end up with like some awful number of slugs or just pounds mass. English units are weird. That's that. But if you actually study physics, you're thinking, actually, that's not what's going on. This is silly. Force is actually the change in momentum over change in time. Now, this is a derivative. This is calculus. I'm not talking about calculus. Calculus is scary, but what this means is small changes of p over small changes of whatever variable you're considering. In this case, it's time. So what's momentum? Well, momentum is the mass of something times how fast it's going. That's it. This is why slow-moving trains can take out cars. There's a lot of mass. Sure, it's going slowly, but your car doesn't weigh much. So momentum equals mv, mass times velocity. Still with me? So now I think we all learned this in physics class. The example of a guy throwing something out the back of his boat, or someone throwing something, right? I'm taking this expo marker and I'm throwing it that way at a certain speed. What's going to happen is, by conservation of momentum, me throwing this is energy going this way, but I gotta have some now too. So if I throw this, let's say 1 kilogram, it's a really dense marker, at 10 meters a second that way, the momentum is 10 kilogram meters a second. Which means I, who weigh, I don't know the number exactly, I'm gonna say I'm 100 kilograms, I'm really fat. Let's go back at 0.1 meters a second, right? Momentum is conserved, so the momentum of the marker is the momentum of me. Same momentum, it's just the values can change. So now, force is change in momentum over time. So, what this is dp dt equals dm dt times v plus m dv dt. Okay? So what does this mean? There's two options for you. Because either your force is the change in mass over time times your velocity, or your mass times your change in velocity over time, or acceleration. So this is the classical way of looking at it, right? But for our rocket engine, right, we have a rocket engine. You are throwing propellant in the combustion chamber and it's going out the engine. It's going out. You're throwing mass in to the engine and the engine's throwing it out, which means you don't have a constant mass. Cool. So that's what your force is. Your force is your change in mass over time times V. What is V? V is the velocity of the gases escaping out the back of your engine. Okay? We clear? This probably isn't that clear. I'm sorry. You just, if you don't like math, just remember the bucket example. That's all that's going on. Really. This is just fluff. But I'm showing off. Right? That's V. So how do we get V? dm dt, you can select. You can choose. No, okay, so again, bucket example, it's all you need, really. The math here is going to get kind of weird. Okay, so we're going to do what's called control volume analysis, just as another way of showing off. If you've done fluid mechanics, so here is our rocket engine going this way because we're being pedantic, okay? So here's our rocket engine. Now, as you all know, rocket engines are 3D, so they have an area here. This is A2. And since this is control volume analysis, here's our control volume. Now, because of combustion, your gas is going out and going to generate pressure. Pressure is force over area. So you have also P2. Now, so we have force coming in. Now what's leaving, we're going to have m dot. That's our change in mass over time. That's easier to write than dm dt. And our V2, because our gases are going out at a certain rate. And then outside we have P3. Now, through conservation of momentum, we can get force. Force equals m dot V2 plus so this is your basic rocket thrust equation. Your force is related to the mass you're throwing out at a certain rate, plus the pressure of gases going out compared to the pressures outside times the area of the nozzle, right? Because the pressure outside wants to come in, the pressure outside wants to go out. So if you have higher pressure outside, it's going to kind of work its way in. You're going to lose some thrust there. But there it is. That's that. Okay, so how do we get P2, A2, m dot, and V2? This is where I can't really do much. I can just show you things. Because I don't have 3 years to explain to you control volume analysis, fluid mechanics, thermodynamics, aerodynamics. I can't do all that. Uh-oh. So instead, what I'm going to do is kind of sum up things just to give you a taste of what really goes on. Okay, so the bucket approximation works, and we have to work with the nozzles now. Right? Our rocket engine has a converging and diverging nozzle. It gets smaller and gets wider. And we all know how nozzles work, right? And you play with them like a garden hose, right? You turn it on, you're holding it, and water's coming out at a certain rate, and then you put your thumb over it, over the exit. You notice that the water comes out faster, right? Why? Conservation of momentum. It's related to the area of something, right? When it's got area this big, it's coming out at a certain velocity, assuming we have the same density. And then you put your thumb over it, you're cutting that area down by a lot. Well, since momentum in equals momentum out, your fluid has to go a lot faster outward to conserve momentum. Same principle, but by converging, diverging. There's a strange phenomenon called a de Laval nozzle. I'm going to draw it here. And it's a really bad drawing because I can't draw. This is a de Laval nozzle. And right here is the thinnest spot called the throat. This is important because a de Laval nozzle is what happens when you have your fluid at the throat, the thinnest spot, going the speed of sound. So right here, m equals 1. Weird things happen with m equals 1 at the throat. Okay? Now, I can't explain all of this because that's aerodynamics and thermodynamics with some fluid mechanics because air is a fluid. But what happens here is if your flow is coming in, so this is in, and if you do what's called an isentropic relation, it's just fancy for something to do with heat loss. Even I can't remember it because thermodynamics is witchcraft. If your flow is coming in at m is less than 1, so it's coming in at slower than the speed of sound, it's going to leave at faster than the speed of sound. Why is this important? Well, remember, F equals m dot v2. V2 is this m. So if you get a really big V2, your force goes up. That's important. Now, what does this mean? How do you get this? Well, there's a few ways to do that. Pretty much what it boils down to is you need a lot of temperature and pressure to get the flow wanting to go out really fast, which you can get through combustion. Now, I'm going to throw equations at you because that's all I can do at this point. So the big governing one for your rocket engine, not the rocket engine, the de Laval nozzle, is dA over A times, so you have to look at, I have a note sheet because you is equal to 1 over 1 minus gamma m squared equals dV over V. Okay, so what we're looking at here is the change in area, aka for our nozzle, the area, right? Because this is a 3D, it's a horrible drawing of it. For our nozzle, right, you have an area since it's a 3D object. Or a really weird looking bow tie, right? So your change in area over your area times 1 over 1 minus gamma. Gamma is a ratio of specific heats for your fluid. So for like air, it's 1.4. For combustion products, it's 1.2. It's a constant, sort of. Times your Mach number is equal to the change in your velocity over velocity. See, it's simple, obviously. But pretty much that's what governs it. This is what says if you hit Mach 1 at the throat, go slower in, you'll go faster out than the speed of sound. Or if you go faster than the speed of sound in, you'll go slower on the way out. That's not clear, I know. But with this, you can get a few relations here. You can figure out the ratio of the pressure here to the pressure out here, so you can get your P2. And then P3 is a given because it's external. But P2 comes here, and you can calculate it based on your combustion chamber pressures, the area, and the Mach number. So an important part of the rocket engine is the area ratio, which is this, which is just A exit, or A2, for area of the throat, the thin part, is equal to 1 over ME at the exit, so that's the Mach number at the exit, times 2 over gamma plus 1 times 1 plus gamma minus 1 over 2 M2 squared times 2 the gamma plus 1 over 2 gamma minus 1. These are icky numbers, but with this, once you get the area ratio and you have this, you can calculate the temperature of your combustion chamber, the temperature going out, the temperature at the throat, anywhere on this nozzle. Once you can do that, you can do anything. Except make friends. But if you use this, you will end up with V2 plus 2 minus P3 A2. And just for clear, so this would be like kilograms a second. V, of course, is meters a second. And this is force over area times the area, so that gets a force. And then you multiply that, you end up with force as well. Again, it depends on your units, but that's just pedantic. Now, one more thing, just so we're all clear, just to get M dot. M dot equals pressure at the throat, area of the throat, over square root of the temperature at the throat, like PV equals nRT. That governs a lot of things, actually, times gamma over R, which is the universal gas constant, which you can look up anywhere, times, gamma over 2 minus gamma plus 1 over 2 times gamma minus 1. That's your mass flow rate. If you work it out, you end up with the right units. That's actually something you should remember for physics or any classes. Make sure your units all multiply out. So now we got the math. I erased the math. It's okay. It can't hurt you. This is a rocket engine. Fuel and oxidizer come in. They explode. Kaboom. This generates temperatures and pressures. Now, which creates a force that pushes upward. Now, the gases are channeled through this nozzle. And because they're channeled through this nozzle a certain way, they come out at a certain speed with a certain pressure. Okay? So F the M dot comes from the oxidizer and fuel coming in and blowing up. The V comes from the oxidizer and fuel blowing up at a certain temperature with certain constants and the shape of the nozzle. P2 is determined by the explosion and the shape of the nozzle. P3 is outside, and A2 you can choose for however you're building your rocket engine. And that's it. Really, on a basic level, that's it. And if I don't make sense, I'm sorry. There's also an internet. You can use that for your help, I guess. Of course, I've made a bold assumption here, assuming that a conspiracy theorist will listen to any of this and follow what I'm saying and not go completely insane and ignore me or have a mental block. It's a big assumption of me. Good job, me. What am I doing with my life? Okay, so I did forget one thing, and that's if you look at the equation for force, P3 can equal 0. So that's a vacuum, essentially. Now that means if you work out the numbers for it, a rocket engine will always have the greatest amount of thrust in vacuum. It's just like our bucket example. The bucket in space will do best because there's nothing else pushing on it. So if you look at any rocket engine, they'll perform best in space. Rocket engines work in space. Voila! I've proved it with math. I drew pictures, I did examples. They work in space. So there we go, conspiracy theorists. That's one. I'm the pressure-fed astronaut. I have a degree in aerospace engineering. I know about rockets and space travel. I have a big history I'd love to share. I know what I'm talking about, and I like math. That's pretty much it for today's video. Next time, we'll be looking at explaining to Jeranism why there isn't a live stream from the surface of the moon. All right, thanks for watching. If I have made a mistake, feel free to point it out. I am always willing to be corrected, unless it's something dumb like a conspiracy theory. But feel free to point out mistakes and errors I've made, or request for clarification. I love explaining things. And I do have one thing before I go. See the Saturn V model I have? There's something wrong with it. So I'm going to take it apart here. We're going to ignore this part. Ignore the launch escape system and the scaling. There's something else wrong with this. I want you to find it. So here we go. Here's the first stage. We have our second stage. And we have our third stage. It looks like I'm flipping off, but I'm not. What's wrong with it?